Welcome to this explainer. Today, we're diving straight into the fascinating mechanics of how AI actually learns to categorize our world. If you've ever wondered how your inbox magically knows what's spam and what's actually important, well, you're in the right place. We are popping the hood on a foundational algorithm called logistic regression. We're going to strip away all that dense jargon and just look directly at the mathematical gears turning inside. Here's our quick roadmap for today's journey. We'll start by defining the classification problem, see why our old tools are kind of broken for this, introduce the sigmoid solution, look at the underlying math engine, and finally end with a pretty massive coincidental plot twist. Let's get right into it. Section 1, the classification problem, or predicting categories. Up until now, you're probably pretty familiar with regression problems, right? That's where we use a sliding scale to forecast something continuous, like the price of a house. But the classification problem, that is an entirely different beast. Here, we're literally forcing the AI to sort things into strict, distinct buckets, no in-betweens. So, the absolutely crucial point here is that we're dealing with binary scenarios. Our AI has to make a hard, definitive choice between exactly two values. 0 and 1. Think of a spam filter. 0 represents our negative class. That's your normal, safe email from your boss. 1 represents the positive class, which is, you guessed it, spam. And just a quick terminology refresher. That correct answer, that 0 or 1, is what we call the label for our training example. Moving on to Section 2, the broken tool, and exactly why linear regression fails us here. Now, you might be sitting there thinking, hey, we already have fantastic algorithms for predicting numbers, like linear regression. Why not just use what we already know? I mean, why invent a whole new algorithm just because our numbers happen to be zeros and ones? Well, it turns out trying to force the linear regression algorithm to predict discrete values ends up breaking the tool completely. Let's actually visualize how it breaks. Imagine we try to jam a straight line onto our category data. The logic seems okay at first, fit the line, and if the output is above 0.5, round it up to 1. Below 0.5, round it down to 0. And honestly, in super simple cases, this might kind of work. But look what happens at step 3. If we introduce just one single outlier to our dataset, like, say, a wildly obvious piece of spam that sits way outside the normal cluster, that straight line tilts drastically just to accommodate it. And that tilt, it completely ruins our decision boundary. Suddenly, your totally normal emails are getting flagged as spam just because of one weird outlier. Plus, let's be real, it just feels unnatural mathematically. A straight line goes on forever in both directions, right? That means it could give us outputs like -50 or +500. That makes absolutely no sense when we strictly need a probability between 0 and 1 to figure out if an email is actually spam. Which brings us to Section 3, the sigmoid solution, or squashing the input. Meet the sigmoid function, also known as the logistic function. This is without a doubt the absolute hero of our explainer today. Notice the specific terminology we're using here. This formula takes literally any input, no matter how massively huge or wildly negative it is, and it squashes, forces, and compresses it into an output precisely between 0 and 1. Because the output is safely squeezed into this permissible range, we can officially, mathematically interpret the AI's output as a true probability measure. If you visualize this, the sigmoid function doesn't give us a rigid straight line. It draws this incredibly elegant S-curve. As your input grows, the curve flattens out, or asymptotes, towards 1. As the input drops, it asymptotes towards 0. And right smack in the middle, it cleanly crosses the y-axis at exactly 0.5. It's brilliant because it gives us a perfectly smooth transition between our negative and positive classes without ever overshooting the bounds. On top of that, it has this incredibly elegant mathematical derivative, which is going to be super important for how the AI actually learns. All right, Section 4. The math engine and maximizing likelihood. So, to fit the parameters for our model, we have to calculate the probability of our labels being correct. But because y can only be 0 or 1, we actually end up with two separate probability equations that complement each other. Step 1 shows us this incredibly nifty exponentiation trick to combine them. Since y is always exactly 0 or exactly 1, when we use y and 1 minus y as exponents, one side of the equation is always raised to the power of 0. And as we know, anything to the power of 0 is 1. So that half of the equation literally just switches off. It's exactly like flipping a light switch to 0. It's just a beautiful way to compress two equations into one. From there, we determine the likelihood for the whole dataset, and our ultimate goal is to maximize that probability, Specifically, we want to maximize the log likelihood. This brings up a super fascinating contrast in how the AI actually learns. In a linear regression, we use an optimization algorithm called gradient descent. The AI is actively trying to minimize its errors, which you can visualize as trying to hike down to the absolute lowest point of a valley. But logistic regression? Totally different game. Here, we are using gradient ascent. Because we're trying to maximize the log likelihood, meaning maximizing the probability that our model is actually correct, the AI is essentially trying to climb up to the very peak of a mountain. And that brings us to our final section, Section 5, the coincidental plot twist and a hidden connection. Once we take those derivatives to find our optimal parameters, climbing that hill to maximize our probabilities, we arrive at this exact mathematical rule for updating our AI's parameters. This is the stochastic gradient ascent rule. Now, I know it looks a bit complex on the surface, but it essentially just tells the AI exactly how large of a step it needs to take based on the difference between the actual label y and our predicted hypothesis. But hold on a second. If we compare this brand new, seemingly distinct rule to the update rule we used for linear regression, they're identical. Seriously, it is the exact same equation structure. Think about it. We started this explainer by completely throwing out linear regression because it was fundamentally broken for classification. We brought in a whole new S-curve function, we used a totally different probability switch trick, we swapped from minimizing errors to maximizing likelihoods, and yet, after all of that, we arrived at the exact same update rule. No way, right? Well, as our source material explicitly points out, this is absolutely not a coincidence. The fact that a radically different algorithm designed for a completely different problem uses the same update structure reveals a massive secret about machine learning. Both of these tools, linear regression and logistic regression, they actually belong to a deeper, hidden family of mathematical laws called generalized linear models. They're basically just different branches growing off the exact same mathematical tree. And that leaves us with a pretty profound thought to ponder as we wrap up. We just watched how the math beautifully folded in on itself, seamlessly connecting predicting house prices to filtering out spam emails. So if radically different AI tools are actually governed by the exact same underlying mathematical blueprint, what other hidden universal rules are quietly running the technology of our future? It really makes you wonder just how deep the mathematical structure of AI truly goes. Thank you so much for joining me in decoding logistic regression today. Keep questioning, keep learning, and I'll catch you in the next explainer.